Now picture uranium isotopes like a bowl of jelly beans. Okay, so here we're imagining a bowl of jelly beans. You have 0.7% U-235, so you have 1,000 jelly beans essentially, and 7 of those will be red jelly beans. Those will represent the U-235. The blue ones will represent the rest, and that's the U-238. So you have 7 red jelly beans, and all the rest are blue, representing U-238. Now remember, highly enriched uranium is when you increase the proportion of, let's say, red jelly beans, or U-235, to U-238. So you're increasing the red ones to the blue ones. When uranium is mined, as you know, it's only about 0.7% U-235 and 99% U-238. You need to remove the U-238 to increase the proportion of U-235 to U-238, right? You want to actually, to increase the proportion of red ones to blue ones, you have to actually remove the blue ones. So let's start with those 7 U-235 and 993 U-238, so that you have 1,000 marbles, or jelly beans. Now let's start by thinking about enriching from 0.7% to 5% uranium. So to get to 5% LEU, how many blue marbles do I need to have? That's really the question that I want to answer. Remember that before we started with 1,000 total marbles, whereas 7 are represent the U-235, they're the red ones, and the rest is U-238. Okay, so to get to 5% LEU, how many blue marbles do I need to have? Well, you want the proportion of red to red plus blue, number of red ones to the number of red ones plus blue ones, to be equal to 5% or 0.05. Okay, so if you now have 7 divided by 1,000, it's 0.7%. You want to increase that to 5%. So the answer is that 7 marbles divided by 140 is equal to 0.05. So it means that you had to go from 993 blue marbles to 133 marbles. So it's actually a very large step that you had to go from 0.7% to 5%. You had to go from 993 to 133. So you need to pull out actually 860 uranium-238 marbles to get to 133 blue marbles left. So the point is that a large part of the work is actually done in the first step to go from 0.7% to 5% HEU. Okay, it's the first big step. And then you might ask, because nuclear weapons, such as a gun-type weapon, will need about 93% uranium-235. So the proportion of U-235 is very high. So now the question is, to increase to 90% U-235, how many U-238 do I have to pull out of this bowl? Well, if it's 90%, then it means it's 7 U-235 divided by 7 U-235 plus 1 U-238. So there's basically only 1 U-238. You've pulled all of them out except for 1 U-238. So you're going from 133 that you had at 5% to 1. So you need to subtract 132 more, which is a big improvement from 853. So the point is that actually the very first step in the enrichment process, where you go from 0.7 to 5%, and 5% is where nuclear power reactors work. So nuclear power reactors actually use 5%, about 3 to 5% enriched uranium. The big step is actually to go to 5%, and it's not so hard to then enrich from 5% to 90%, which you could use for nuclear weapons. And that's why we should be concerned about the whole process of enrichment. Now, one important note is that we keep on talking about uranium-235, not plutonium-239. And the question is why? Because these two isotopes are often used in nuclear weapons, U-235 and plutonium-239. Why can't you use plutonium-239? And again, you have to sort of think like a neutron. Let's talk about the concept of pre-detonation or triggering the bomb to explode before the optimum conditions have been established. So the optimum conditions are when you're assembling these two half-critical masses together into one critical mass, and you know, you cause the fast chain reaction to happen. Well, what can happen if you have a lot of neutrons flying around? So there's a lot of neutrons that are happening as these two subcritical masses are coming together. Then you get pre-detonation. So you haven't actually reached the optimum point where the two pieces come together. It pre-detonates, and part of it will explode, but you won't necessarily reach the critical mass where you get the real powerful explosion. So that's not good from a nuclear weapons point of view, from a nuclear weapons design point of view. Now, if we now examine the different isotopes, if you look at the different nuclides, you have U-235, U-238, plutonium-239, plutonium-240. We look at the number of spontaneous fissions. So this is the spontaneous, this is the when fission happens, not because of the fact that you're inducing it with neutrons, but fissions happen just spontaneously as a kind of a part of the normal decay of the isotope. Now, if you look at spontaneous fission per kilogram per 100 microseconds, okay, so very short slice in time, you're looking at, in that very short slice in time, how many spontaneous fissions would happen. If you have spontaneous fission, then you have neutrons coming out, and this would cause pre-detonation or detonation of the bomb before the optimum conditions have been established. Now let's look at that here. So you have U-235 here. The spontaneous fission per kilogram per 100 microsecond is really, really small. This e to the minus 7 really means 10 to the exponent minus 7. So 5.6 times 10 to the minus 7. It's really small chance that this will happen. So the spontaneous fission per critical mass per 100 microseconds. So if you would assemble critical mass, the probability that you would get one neutron coming in there that would cause pre-detonation is really very low. That's what this is showing. It's the number of spontaneous fissions that you would have per critical mass per 100 microseconds. Now if I compare it to plutonium-239, it's also quite low, but there's still a possibility that it could happen. If I compare it to plutonium-240, now look at this. Plutonium-240 has a very different half-life in terms of spontaneous fission than uranium-235. Do you remember the spontaneous fission for U-235 happens very, very rarely? That's not true for plutonium-240. It has a very short half-life compared to U-235, and so the number of spontaneous fissions that you would get per kilogram is more like 48. And the spontaneous fissions per critical mass per 100 microseconds. So if you imagine them, these two pieces assembling, and it's 100% plutonium-240, would be 822 neutrons per 100 microseconds spontaneous fissions. So this would be not good from the point of view of nuclear weapons design, because you don't want it to pre-detonate. Because you haven't reached the conditions where you actually get the explosive chain reaction. So plutonium-240 is actually what you don't want to have in nuclear weapons. You only want plutonium-239. But as we'll talk about, plutonium-239, to make a bomb out of plutonium-239, you have to use a completely different technique. The problem is that you can't smash these things together fast enough so that you can be sure that there's not going to be neutrons that are going to cause an inadvertent pre-detonation of the bomb. So that's really why plutonium-239 will not work in a gun-type design, because you can't smash these things fast enough together, these two half-critical masses together, so that you have enough time that you can actually cause the chain reaction to happen before you get sort of a little neutron that comes in there and causes it to happen inadvertently. So what's the solution to that? Well, you have to assemble it very quickly, so the probability of a stray neutron that just comes in there because of spontaneous fission or other neutrons, is low and the bomb won't be detonated. So you need to do it very, very fast, and a gun type weapon design is not good enough. So what they used, and this was the bomb that's dropped on Nagasaki, is an implosion type bomb. For this they used plutonium-239. Remember, the important design criteria is you want to prevent neutrons from escaping, you want to increase the probability of fissions to happen, and you want to prevent the neutrons from absorption. So what you needed to do, instead of having two pieces that are half critical mass coming together very fast, instead of that, what you do is you have explosive lenses and you cause explosions to implode. Now remember the crowded room analogy. In the crowded room analogy, I said that if you increase the density of the fissile material, of the U-235, or in this case the plutonium-239, then you have a higher probability of fissions to happen and for a chain reaction to happen. So that's what they did with the plutonium-239, with the implosion type weapon. They increased the density of the plutonium-239 to increase the possibility of a chain reaction, for a chain reaction to happen. So you can see that here. The design is basically that you have the fissile material in the center and that you have explosions here that are on the outside. And basically you're squeezing this down very, very fast. These explosions implode. It causes this to rush towards the center, this to move to the center, this, like this soccer ball, to sort of implode towards the center. And that causes this plutonium metal to actually compress and increase the density. And once you're increasing the density, it causes the plutonium-239 nuclei to come closer together to the other plutonium-239. And so then it's exactly like the crowded room analogy. And you would have a high probability of producing fast fission chain reaction. So for an implosion type weapon, it's a little different. What you're doing, instead of taking two half critical masses and bringing them together, you're increasing the density. I kind of tried to show that here. So this is the fissile material, in this case HU or plutonium, that's reaching critical mass. If it's this big here, right, then the nuclei are so far apart that when you have a fission happening, the neutrons just tend to escape. They can't find the other U-235 or plutonium nuclei. They're just too far apart. But if you collapse them and compress the material and bring it close together like this, right, then the U-235 or the plutonium are so close together so that the neutrons that's produced through a fission will find another U-235 to split, and so you get the chain reaction continuing. And that's kind of how you have to kind of think of it, and really think in terms of the crowded room analogy that I discussed earlier. So really what you're doing is you're compressing it here, so you have explosives all around, right? And this is really like almost like a fluid. You can think of it like a fluid, that you're compressing this to such high temperatures and pressures that it becomes almost like a fluid or like a water balloon. And so you're squeezing down the water balloon very evenly. Now in this picture, the picture is not very serious, but you kind of see how the water balloon moves. And you can imagine that if you're compressing a water balloon, spherical water balloon, you're compressing it, it's kind of hard to compress because you find that the part of the water balloon will just squeeze between your fingers. And that's what you don't want for an implosion type weapon. And that tells you the challenge of producing a implosion type weapon. We believe that it's so difficult and so challenging that non-state actors or terrorists would probably not be able to do it, and it's really states who can develop these types of weapons. So we can get HU by enrichment. We talked about that. Basically what you're doing is you're increasing the proportion of U-235 compared to U-238. Now what about plutonium? So now let's talk about plutonium production, which is quite different from highly enriched uranium or enriching uranium. In this case, you're not worried about the uranium-235, which are represented here by the red dots. You're not worried about enrichment of the U-235, but you're worried about the U-238 producing plutonium-239. And I'm going to talk about that now. So here I'm showing a picture of similar as I did before, but here the blue dots are the U-238 and the red dots are the U-235. Right? And in power reactors, you have about 3 to 5% uranium-235. So that's the power reactors are the nuclear reactors that you would use to produce electricity. For a gun-type weapon, you actually enrich this part. You enrich the U-235. Now, for an implosion-type weapon or a plutonium-type weapon, what you worry about is actually the U-238 component. Because through neutron interactions with the U-238, you can actually produce plutonium-239, which is the fissile material that you worry about in an implosion-type weapon. Let's see how that's done. So in the nuclear reactors, you have neutrons everywhere, right? And if you have uranium-238, which is present in the nuclear fuel, if you have uranium-238, it can capture a neutron like this. So a neutron plus a uranium-238 can produce uranium-239. And this has a very short half-life of 24 minutes. When this decays, it can produce neptunium-239. And when that decays, that has a 2.4-day half-life, it will decay to plutonium-239. So here you have gone from U-238 to plutonium-239. You've converted from uranium metal into a plutonium isotope. And this is directly usable for an implosion-type weapon. This is called a fertile material because fertile materials are materials that you can actually convert into a material that can sustain a chain reaction. Because U-238 itself can't sustain a nuclear chain reaction. But by capturing a neutron, it can become plutonium-239, which can sustain a chain reaction. So here you kind of see that picture here, that you still have the U-235, but then you're producing these little black dots, and that's the plutonium-239 that's produced, and that you would use in an implosion-type weapon. Now, one important thing, and I think we'll talk about that later, is if this plutonium-239 hangs around for long enough, then it will also capture a neutron, just like the U-238 captured a neutron, and then it becomes plutonium-240. Remember, a neutron is not a proton. So a proton is how you change the element from one element to another, from hydrogen to helium, right? From hydrogen to helium, you switch from having one proton to two protons. In this case, you're capturing a neutron. So what you're changing is, you still have the same element, but you're changing the amount of nucleons that there are, the atomic mass. So you're changing it from 239 to 240. Now remember the table that I showed you earlier. Plutonium-240 actually behaves very differently from plutonium-239. It has a very different half-life and a very different spontaneous fission half-life. And so what this means is that you can produce a lot of neutrons coming from plutonium-240, and is that plutonium-240 produces a lot of neutrons. It decays and then it produces a lot of neutrons, and this is exactly what you don't want to have in a nuclear weapon, because then you get this inadvertent possibility of having an explosion or pre-detonation. You call this a fizzle, and when you talk about nuclear weapons, and so that's why you want to decrease the proportion of plutonium-240 compared to plutonium-239, and we'll talk about that later. Now let's just talk about some definitions. Fissionable means a nuclide that undergoes fission after neutron capture. Fissile is a nuclide that can sustain a chain reaction. So fissile materials can sustain a chain reaction, like U-235 or plutonium-239 or uranium-233, and so on. A fertile material is a nuclide that can become fissile after irradiation in a reactor, such as uranium-238 that I showed you here, where you can capture a U-238 captures a neutron and then can become plutonium-239. So the trick is that plutonium-239 absorption of a neutron converts it to plutonium-240, and since it has a high spontaneous fission rate, it's not good for nuclear weapons. So produce weapon-grade plutonium, you need to remove the plutonium fuel before it becomes plutonium-240. And so you can already picture that if you leave the material like plutonium-239 after it's been produced, and you leave it in the reactor for a long time, then the probability is high that it's actually going to capture the neutron. And so what you want to do is to produce weapon-grade plutonium is to actually pull it out of a reactor very quickly, so it doesn't, high proportion of it doesn't become plutonium-240. So weapon-grade plutonium is actually when it's less than 7% plutonium-240, so that the spontaneous fission rate is relatively low. Now there's a very powerful policy analysis rule of thumb for actually calculating the amount of plutonium that's produced in a nuclear reactor. And the rule of thumb is like this. The 1 megawatt days of operations of a reactor produces about 0.9 grams of plutonium in any reactor using 20% or lower enriched uranium. So let's see how this rule of thumb is applied. So let's say the typical power reactor has 2650 megawatt power. So that's how much power it actually produces. And capital M, capital W is short for megawatts, or 1,000,000 watts. So now let's calculate the mass of plutonium-239 that's produced. Well, we have a power of 2650 megawatts, and it runs for about 45 days. Then it's 2650 times 45 days, and you calculate out to be 119,250 megawatt days, so 119,000 megawatts days. Now you want to convert that megawatts into grams plutonium. So you simply just multiply the 0.9 grams per megawatt days times the 119,000 megawatt days. And what you get is you get 207,325 grams plutonium. That's how much is produced in a powerful power reactor when you run the reactor for 45 days. Okay. So it's basically, if you convert this now, you can convert to kilograms, and 1,000 grams is equal to 1 kilogram. You would produce 207 kilograms plutonium in only 45 days running a very powerful reactor. So you can see that you can actually produce plutonium in power reactors very quickly. And if you think about the significant quantity, or the quantity that you would need to actually produce a nuclear weapon, by the IEA this is about 8 kilograms, but in fact modern boosted fission primaries is kind of a modern type of weapon, actually uses only about 4 kilograms of plutonium. So only 4 kilograms of plutonium. So that means that when you run a reactor, a power reactor for about 45 days, you produce many more mass of plutonium than you actually need to produce a nuclear weapon. And that's why it's so important that safeguards, IEA safeguards, check to make sure that power reactors are not actually producing plutonium. That's why this whole safeguard system, integrated safeguard system, is in place. Let's make another example here. A company is making a proposal to sell one turnkey LWR, that's a light water reactor, of 2,700 megawatts to Burma. You're the one who is responsible for deciding whether a reactor project should proceed from the point of view of proliferation of the nuclear technology to that country. The official, in a condescending way, claimed that this particular reactor will in 1 month not produce any plutonium, so that there are absolutely no risks or worries that should concern you. What would you say, hopefully in a polite way, in response to the official about how much plutonium is produced in this reactor per month in terms of scheduled quantity? A significant quantity. A significant quantity for plutonium is about 8 kilograms. Okay. So 1 kilogram is equal to 1,000 grams, and the rule of thumb, as you remember, is 1 megawatt day of operation produces 1 gram of plutonium in any reactor using 20% or lower enriched uranium. So here's the answer to our question. Since the rule of thumb is 1 gram produced per megawatt days, in 30 days, because we were really interested in 1 month, as you see here, the official in a condescending way claimed that this particular reactor will in 1 month not produce any plutonium. So that's what we're really doing. We're going to calculate how much plutonium is produced in 1 month. So in 30 days, which is 1 month, the reactor produces 2,700 megawatts times 30 days. That's how much megawatt days are actually produced. So it's 80,000 megawatt days. Now we apply the rule of thumb. 80,000 megawatt days, right, is 80,000 times about 1 gram plutonium per day. So if you calculate it all out, you get about 80 kilogram plutonium. So we produce 80 kilograms plutonium. So in terms of significant quantity, this is 10 significant quantities, which is enough roughly for about 10 bombs. So just in 1 month, this particular reactor, go back here, the particular reactor would produce about 80 kilograms plutonium. So it's absolutely not true that you don't produce any plutonium in 1 month. Okay, so this should be your answer. Excuse me, but your assertion that a 2700 megawatt reactor will produce only 100 grams plutonium per month is simply not correct. In fact, if you go through the calculation, which I just did while you were talking, you will find that the reactor you propose produces about 10 scheduled quantities per month. And the whole room would be very, very quiet because they're very impressed with your knowledge. Now let's look at this picture here. Now remember what I told you about plutonium production in a reactor. If you want to produce plutonium and you want to produce weapon-grade plutonium, then you have to pull the fuel out pretty quickly. About a month or maybe 2 months afterward, you pull the fuel out, because that's when you're producing weapons-grade plutonium. So if you look at these two pictures, right, the one left side you see a power reactor with the plume. So you see that here. You see the reactors itself here, and here you see a plume of smoke. And this means that the power reactor actually is running. Right? This is the cooling tower. The power reactor is running, and you see that this steam is coming off of the tower. You see the shadow here, and you see the smoke. Well, it's not really smoke, but the steam, you see that here. Now, in this case, you look on the right side, and you notice that there's no steam coming from the reactor. It's exactly the same reactor, but there's no steam. So you ask yourself the question, what's happening here? Well, what could be happening is that they could be refueling. But if you find out that they're refueling often, that it means that they might be producing plutonium and pulling out the fuel and replacing it with fresh fuel, and actually taking that fuel and taking out the plutonium. So this is one of the things that non-proliferation analysts actually look at, is one of the signs that reactor may be producing plutonium. Now here's an important quote that I always remember. This is what Robert Oppenheimer said after the first Trinity bomb, and this was a plutonium implosion bomb. I remember the line from the Hindu scripture, the Bhagavad Gita. Vishnu is trying to persuade the prince that he should do his duty, and to impress him he takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds." I suppose we all thought that one way or another. This is how Robert Oppenheimer reflected on the Nagasaki, on the Trinity shot, on the plutonium bomb. So this is a summary from Module 2, Chapter 3. It's important to think about what are the advantages and disadvantages of these different ways of making nuclear weapons. Uranium, or an HEU-based weapon, has the advantage that testing is not necessary, and this is why it's a concern from the point of view of non-state actors or terrorists. This would probably be the choice of weapon for them, because it's so easy to build. The disadvantage with this type of weapon is that it's very difficult to get HEU, and that is so important that globally we manage methods, we figure out methods to make sure that HEU is not being used for bad purposes, and that we minimize the amount of HEU that's being used around the world. The other material and the other method of making a weapon is using plutonium. Plutonium-239, as I said, is the important isotope which you would want to use. Now, in this case, it's easy to produce. I showed you that in the reactor it's produced. It's not enriched. It's not like HEU, where you enrich the amount of U-235 compared to U-238, but instead you actually produce it in a reactor. So the U-238 captures a neutron and then becomes plutonium-239. Disadvantage of this type of weapon is that testing is necessary, and this is why we think that it's more states would develop this type of weapon, and not terrorists, because it's such a sophisticated weapon.
Please go to the next video.